Hey, we're the consensus team, and I'm Carrie.
Hi, I'm Tally.
I'm George.
I'm gonna briefly explain what consensus is and why it's important. So imagine you're a business and you have a client, and the client sends you requests, and you process the requests and you store them somewhere, right? Um, to do this, you have a server that does everything for you. But also imagine that the server crashes. And at that point, since you only have one server, your business stops, comes to a halt, and the server may or may not have like lost information. Um, and so that's not really okay. So what you can do is you can have multiple servers to serve as backups so that when your primary server crashes, another server just takes its place, right? But another problem is that what if the server doesn't just crash, but it's actually malicious? At that point, you need a way so that the two honest servers can still agree with each other to come to like a conclusion on what to do. And the way that these servers like find agreement is called, or it's handled by consensus protocols. And so by decentralizing information like this between servers, between multiple servers, um, we provide immutability, privacy, security, and transparency. And so the current protocol used in the field is based on Paxos, and it's called Practical Byzantine Fault Tolerance, PBFT. And there's another version called Scalable Byzantine Fault Tolerance, which is SBFT. And so the way, what do you call it? PBFT right now works in partial synchrony, and it works for up to 1/3 of the total servers being faulty. And by working in partial synchrony, it basically, in a synchronous setting, it guarantees that the servers always come to an agreement, given that there aren't more than 1/3 faulty servers. And in an asynchronous setting, it guarantees that the servers are always doing something and they're not just being complacent.
The protocol we are implementing is called Sync-HotStuff. It operates in the synchronous world. The reason why you want to replace the SBFT implementation using this protocol is that it tolerates up to 1/2 Byzantine replicas, while the original implementation by VMware only tolerates 1/3. In addition, it does not require lockstep execution in the steady state, meaning that we do not require all replicas to perform the same step at the same time. Last, it handles a more realistic synchrony model. The SBFT implementation actually runs in partial synchrony, which the optimistic fast pass is indeed fast, but the problem is that it does not tolerate any failed replicas. Therefore, it is to some extent unrealistic. We believe that the Sync-HotStuff implementation will solve this problem. There are basically 3 steps in Sync-HotStuff. The first step is propose, which the leader proposes a command including the client message and view number, etc. And then on receiving the first valid proposal from the leader, a replica will broadcast a vote for it. And when it votes, it also forwards the leader's proposal to all other replicas. In this way, the system will be able to detect any leader equivocation and start view change if necessary. Last, if a replica does not receive a proposal for a conflicting command in 2 delta time, after voting, it will start committing the command. For our project progress, the first 2 weeks, we try to understand basics of consensus protocols, including various types of failures, like crash failures, omission failures, and finally Byzantine failures. We also read several papers about SBFT and Sync-HotStuff so that we'll be able to understand the protocols more efficiently. In weeks 3 and 4, we set up the local and remote environment and started reading through the code base to understand the current SBFT implementation. We also met with the VMware programmers so that they could help us address some of our concerns and questions. The next 2 weeks, we started implementing and testing minor changes to the current implementation. We tested a 3-run protocol that mimics Sync-HotStuff and tested the implementation that forces the protocol to run only in slow paths, and the implementation that alters the fault tolerance from 1/3 to 1/2. In the final 4 weeks, we started implementing and testing the steady state of Sync-HotStuff, which includes propose, vote, and commit steps.
As George had just discussed about the project timeline, I would like to dig more into what we have done most recently, the implementation of the steady state Sync-HotStuff protocol. So let me start from the most basic and also the most different part of Sync-HotStuff implementation to SBFTs, which is its message classes. Sync-HotStuff is more concise in the design and only takes 2 communicated routes to reach a consensus. It's only these 2 message classes, proposal and vote messages, while SBFT actually needs up to 30 message classes in total. So vote message is what the replica broadcasts to all other replicas, but it didn't notice any error from the primary. So it is just a signature that is unique to each replica. While proposal message actually contains 2 things. First is a pack of client requests to be reached consensus upon, and also the certificate of from the previous round, which is a combined signature that has been collected by the replica from its peers. Having implemented the message classes, we then move on to the specific rounds in the protocol. So, which is sending and processing the proposal and vote messages, and also executing the client requests contained in the block. The most challenging part was actually to work with the current code base we had. So as it didn't provide an existing clear encapsulated interface that separates the protocol part with the rest. For example, many methods in the protocol implementation are tied closely to signature collector, controller, main log, and other classes. So we had to be very careful in modifying the existing code structure and not to change something important to the code base. For example, the thread pool. I think many previous exploratory work we did to get hands-on experience with the code base actually help us a lot in this phase. So in the future, as we all hope to continue our work in the summer to the new semester as independent study, we will continue to work on it. Mainly working on to implementing view change in the Sync-HotStuff protocol. So view change happens when other replica detect problematic behaviors from the current leader. For example, the leader crashes, such as no longer sending new proposals to replicas, only had Byzantine failures, such as it sends different proposals to different replicas. So we'll be implementing how the replicas can handle these scenarios, like how it detects the failure for the primary, and then how it broadcasts a blame message to other replicas and quit the current view. We'll also be implementing how they collectively enter a new view and also update their latest committed work to the new leader to enter the steady state again. Also, after the implementation, we plan to design metrics and networking scenarios that are interesting and to test and evaluate the performance of the 2 protocols and to see whether we can produce a new and contributive insights. So that is of our presentation. If you have any questions, feel free to DM us, and we'll be glad to answer them.